Welcome to this problem walkthrough. In this session, we'll tackle LeetCode problem number 269, titled Alien Dictionary. This is an intriguing problem where we'll determine the order of letters in an alien language based on a sorted dictionary of words. Let's explore the logic, approaches, and techniques required to solve this step by step. Let's get started. In this problem, we are tasked with determining the order of characters in an alien language. The alien language has its own alphabetical order, which is different from what we use. You are given a list of words from the Alien Language Dictionary, and these words are sorted according to their own lexicographical rules. Your goal is to figure out the order of characters based on this sorted list. If the order cannot be determined or is inconsistent, you will return an empty string. The input consists of a list of strings, where each string contains lowercase English letters, and the total number of characters across all the words combined will not exceed 10,000. The output will be a string representing the new alphabetical order. If there are multiple valid orders, you can return any one of them, and if no valid order exists, return an empty string. To better understand the problem, let's look at some examples. In the first example, we have the input words WRT, WRF, or ETT, and RFTT. The output is WRTF. This order is derived by comparing adjacent words. First, comparing WRT and WRF, the first differing letters are T and F, so T comes before F. Next, comparing WRF and the first differing letters are W and E, so W comes before E. Then, comparing and ETT, the first differing letters are R and T, so R comes before T. Finally, comparing ETT and RFTT, the first differing letters are E and R, so E comes before R. By combining these relationships, we determine the order W-E-R-T-F. The resulting order from the first example is WRTF. In the second example, the input words are Z and X. The output is ZX. This is because when comparing the two words, the first differing letters are Z and X, so Z comes before X. However, in the third example, the input words are Z, X, and Z. Here, there is no valid order because the relationships are inconsistent. While Z comes before X in the second word, Z also comes after X in the third word, which creates a contradiction. In the third example, the output is an empty string because of this inconsistency in the order. The constraints of the problem specify that the list of words will contain at least 1 and at most 100 strings, with each string having a length between 1 and 100. Additionally, all characters in the strings are lowercase English letters, and the total number of characters across all words will not exceed 10,000. If the input order is valid, we are guaranteed to find at least one valid ordering of the characters. However, when inconsistencies like cycles occur, it becomes impossible to determine a valid order, which is why we would return an empty string in such cases. There are a few more details to keep in mind. If there are no differing characters between some adjacent words, the order of those characters remains undetermined, as they provide no new information about their relative positions. Additionally, if the input order is inconsistent, for example, if there are cycles in the graph representation of the character relationships, then no valid order can be determined, and the output must be an empty string. These edge cases highlight the importance of carefully analyzing the relationships between characters to ensure consistency in the derived order. To solve the alien dictionary problem, we need to determine the order of letters in an alien language based on a sorted dictionary of words. The core of this problem lies in finding a valid topological order of characters. Essentially, we can think of each character as a node in a graph, and the precedence relationships between characters as directed edges. To approach this, we first considered a brute force method. The intuition here is to generate all possible permutations of the characters and check which one satisfies the order specified by the dictionary. However, this approach is computationally infeasible due to its factorial time complexity. For even a moderate number of characters, this would become impractical. The more viable approach involves graph representation combined with topological sorting. Here, we represent the problem as a directed graph, where an edge between two nodes signifies that one character must appear before the other. To build the graph, we compare adjacent words in the dictionary and, for the first mismatched character, we create a directed edge. Once the graph is built, we perform a topological sort using algorithms like Kahn's algorithm or depth-first search. This approach is highly efficient, with a time complexity of O, V plus E, where V represents the number of unique characters and E represents the number of edges in the graph. The graph-based approach was chosen because it directly leverages the problem's structure and ensures correctness by respecting the directed dependencies between characters. Additionally, there is an optional extension using a priority queue for lexicographical topological sorting. This comes into play if we need to find the smallest lexicographical order among multiple valid solutions. The intuition here is to use a min heap to process nodes in lexicographical order, always prioritizing the smallest character when breaking ties. While this approach has a similar complexity to the graph-based method, it introduces an additional overhead due to heap operations, specifically an O, V log V, term. However, for the basic problem, this extension is unnecessary as the problem does not require lexicographical ordering. Ultimately, the graph representation combined with standard topological sorting was selected as the best solution. It efficiently solves the problem without adding unnecessary complexity, and it aligns naturally with the constraints and dependencies given in the input. This strategy is built on a few key observations. First, the problem naturally forms a directed acyclic graph, or DAG, because the ordering constraints between characters are transitive. This means that if one character must come before another, and the second must come before a third, the relationship holds consistently throughout. Second, the rule of the first mismatched character is crucial. When comparing two words, the first character that differs between them directly determines the order between those two characters. This simplifies the process of building the graph. Lastly, the efficiency of this approach makes it ideal. With a time complexity of O, V plus E, it is well suited to handle cases where the number of unique characters and dependencies is small relative to the overall input size. Of course, there are trade-offs to consider. The graph-based approach requires careful implementation of graph construction and topological sorting, but it is both efficient and simple once understood. In contrast, the brute force method, while conceptually straightforward, is computationally impractical. The priority queue extension, while useful for lexicographical ordering, introduces unnecessary complexity for the basic problem. As a result, the graph-based approach strikes the right balance between efficiency, simplicity, and correctness, making it the most appropriate solution for the alien dictionary problem. To solve the alien dictionary problem, we start by breaking it down into distinct steps. The first step is input validation. Here, we check if the input is a valid list of strings. If the input is empty or contains fewer than 2 words, the problem is not well defined, and we can safely return an empty string as the result. Next, we move to the graph construction phase. This involves initializing key data structures. We use an adjacency list, which is essentially a dictionary where each character maps to a set of characters it points to. Additionally, we maintain an in-degree dictionary to track the number of incoming edges for each character. We then populate the nodes of the graph by adding all unique characters from the input words and initializing their indegrees to 0. Finally, we add edges to the graph by comparing consecutive words in the input. For each pair of words, we identify the first mismatch between them. This mismatch reveals the ordering constraint indicating that one character precedes another in the alien language. When adding edges to the graph, we create a directed edge from the mismatched character in the first word to the corresponding character in the second word. At the same time, we increment the in-degree of the character in the second word, as it now has a new prerequisite. However, there's an important edge case to handle here. If the first word is a prefix of the second word but is longer, the input is considered invalid. For example, with input words like ABC, it's impossible to determine a valid order since the prefix constraint is violated. In such cases, we immediately return an empty string. Once the graph is constructed, the next step is to perform a topological sort using Kahn's algorithm. To begin, we initialize a queue to store characters with an in-degree of 0. These are the characters that don't have any prerequisites. From here, we process the nodes one by one, removing the front character from the queue and appending it to the result list. For each neighbor of the removed character, we decrement its in-degree by 1. If any neighbor's in-degree becomes 0, it is added to the queue for processing. The topological sort continues until the queue is empty. At this point, we need to check for cycles in the graph. If the result list contains fewer characters than the total number of unique characters, it means some nodes were not processed due to a cycle. This indicates contradictory constraints in the input, making it impossible to determine a valid character order. In such a case, we return an empty string. Finally, if no cycles are detected, we join the characters in the result list to form the alien dictionary order and return it. Now, let's take a moment to reflect on some key insights. First, why do we use topological sorting? This problem essentially boils down to determining a valid ordering of characters based on precedence constraints. Topological sorting guarantees that for every directed edge U appears before V in the final order. Additionally, detecting cycles is crucial because they represent conflicting constraints that make a valid order impossible. Lastly, by checking prefix relationships early during the graph construction phase, we can terminate the algorithm early in cases where the input is invalid, saving unnecessary computation. To implement this algorithm efficiently, we rely on three key data structures. The first is the adjacency list, which represents the graph. This structure is space efficient, especially for sparse graphs, and allows us to efficiently traverse the neighbors of any node. Next, we use an in-degree dictionary to track the number of prerequisites for each character. This allows us to quickly update in-degrees during the topological sort process as edges are removed. Finally, the queue, or deque, plays a critical role in managing the nodes with an in-degree of 0. It enables us to process the nodes in the correct order, ensuring that we respect the precedence constraints defined by the graph. Now, let's analyze the time and space complexity of this algorithm. The time complexity begins with graph construction, which requires O(C) time, where C is the total number of characters across all input words. This accounts for iterating through the words and comparing consecutive pairs. Next, the topological sort itself takes O(V plus E) time, where V is the number of unique characters, and E is the number of edges in the graph. Combining these steps, the total time complexity becomes O(C plus V plus E). For space complexity, the adjacency list and in-degree dictionary together require O(V plus E) space. The queue, which at most holds all nodes, requires O(V) space. Therefore, the overall space complexity is O(V plus E), making the algorithm efficient for this problem. Let's walk through an example to solidify our understanding. Suppose the input words are WRT, WRF, or ETT, RFTT. First, we construct the graph. The nodes are the unique characters, W, R, T, F, E. The edges, determined by comparing consecutive words, are WE, RT, and TF. Next, we calculate the in-degrees, W, 0, E, 1, R, 1, T, 1, F, 1. Starting the topological sort, we initialize the queue with characters having an in-degree of 0, which is W. We process the nodes in order, appending them to the result list, W, E, R, T, F. Finally, we join the result list to get the output, WRTF. This is the valid alien dictionary order for the given input. To solve the alien dictionary problem, we begin by importing the necessary modules, such as defaultDict and deque, to help us construct the graph and perform topological sorting. Inside the alien order method, the first step is to create a graph to represent the character dependencies. We use a defaultDict of sets to represent the adjacency list, and an in-degree dictionary to track the number of incoming edges for each character. The in-degree dictionary is initialized so that each character in the input word starts with an in-degree of 0. Next, we build the graph by comparing each pair of adjacent words in the input list. For each pair of words, we determine the minimum length between the two, and check for a special condition. If one word is a prefix of the other, but the first word is longer, the input order is invalid, and we return an empty string. Otherwise, we compare the characters at each position. As soon as we find two characters that differ, we create a directed edge from the character in the first word to the character in the second word. We also increment the in-degree of the second character to reflect this dependency. After finding the first differing pair, we can stop comparing further characters for that pair of words, as the order is now established. With the graph constructed, we move on to the next step of the solution, which is performing a topological sort. The topological sort is implemented using Kahn's algorithm. We start by initializing a queue with all characters that have an in-degree of 0. These are the characters with no dependencies and can appear first in the order. We also create an empty list called order to store the result. While there are characters in the queue, we process them one by one. For each character, we remove it from the queue, add it to the order list, and then reduce the in-degree of all its neighbors in the graph. If any neighbor's in-degree becomes 0, it means all its dependencies have been resolved, so we add it to the queue. This process continues until the queue is empty. After processing all characters, we check if the length of the order list is less than the total number of unique characters. If it is, this indicates that there is a cycle in the graph, and it's impossible to determine a valid order, so we return an empty string. Otherwise, we join the characters in the order list to form the final answer and return it as a single string. Here, we begin the Java implementation of the alien dictionary problem. First, we import the necessary libraries and define the alien order method, which takes an array of words as input. Our goal is to determine the order of characters in the alien language. The solution starts by creating a graph, which will represent the relationships between characters, and an in-degree map, which tracks the number of incoming edges for each character. We initialize these structures by iterating through each character in the input words. Every character is added as a key in both the graph and in-degree map, with its initial in-degree set to 0. Next, we build the graph by comparing adjacent words in the array. For each pair of words, we determine the minimum length to ensure we only compare characters that exist in both words. At this point, we also handle an edge case. If a word is a prefix of another and the longer word appears first, the ordering is invalid, so we return an empty string immediately. Now, we continue building the graph by comparing characters from two adjacent words. We iterate over the characters up to the minimum length of the two words. When we encounter the first differing characters at the same position, we know there's a precedence relationship between them. Specifically, the character in the first word must come before the character in the second word. If this relationship doesn't already exist in the graph, we add an edge from the first character to the second. Additionally, we increase the in-degree of the second character to reflect this new dependency. Once we finish processing all adjacent pairs of words, we move on to the topological sort of the graph, which will help us derive the character order. To start, we initialize a queue with all characters that have an in-degree of 0, as these characters have no prerequisites. We also initialize a string builder to construct the final order of characters. As we process the characters in the queue, we'll ensure the order respects the dependencies in the graph. In the topological sort, we process characters from the queue one by one. For each character, we append it to the result string and then examine its neighbors in the graph. For every neighbor, we decrease its in-degree by 1, as the current character has now been processed. If a neighbor's in-degree becomes 0, it means all of its prerequisites have been resolved, so we add it to the queue. This process continues until the queue is empty. After processing all characters, we check if the length of the resulting order matches the number of unique characters in the graph. If not, it indicates the presence of a cycle, meaning there's no valid ordering, and we return an empty string. Otherwise, we return the constructed order as the final result. This implementation ensures that we account for all valid dependencies and handle edge cases like cycles and prefix conditions effectively. To solve this problem, we start by initializing two structures, a graph to represent character dependencies and an in-degree dictionary to track how many edges point to each character. Initially, the graph is empty, and all characters in the given words have an in-degree of 0. Next, we build the graph by comparing adjacent words to determine the order of characters. Comparing WRT and WRF, the first differing characters are T and F, so we add an edge from T to F and update the in-degree of F to 1. Then, comparing WRF and the first differing characters are W and E, leading to an edge from W to E and an in-degree of 1 for E. Similarly, comparing R and ETT, we find R and T differ, so we add an edge from R to T and increment the in-degree of T. Finally, comparing ETT and RFTT, the first differing characters are E and R, resulting in an edge from E to R and an in-degree increase for R. By the end of this step, the graph and in-degree dictionary reflect the character relationships and their dependencies. Now that the graph is constructed, we perform a topological sort to determine the character order. Using Kahn's algorithm, we start by initializing a queue with nodes that have an in-degree of 0. In this case, W is the only such node, so it is added to the queue. We process W first, appending it to the order and reducing the in-degree of E, which now becomes 0 and is added to the queue. Next, we process E, append it to the order, and decrement the in-degree of R, making R eligible for the queue. As we continue, processing R appends it to the order and reduces the in-degree of T, which is then added to the queue. Similarly, processing T appends it to the order and reduces the in-degree of F, which is finally processed. At each step, we ensure the in-degree updates and the queue reflect the dependencies between characters. At the end of the topological sort, the order list contains all the characters in the correct sequence, W, E, R, T, F. Since the queue is empty and we've successfully processed all nodes, the final output for this example is the string WRTF. This demonstrates how the topological sort extracts a valid order when the graph is acyclic and all dependencies are resolved. With this, we have completed the first example. Now let's consider two edge cases. In the first, the input words are ABC and AB. Here, the prefix of the longer word matches the shorter word entirely, but the longer word cannot precede the shorter one in a valid dictionary. This creates an invalid case, as no ordering would satisfy this constraint. Thus, the output is an empty string. In the second edge case, the input contains only one word, Z. There are no adjacent words to compare, so the graph remains empty, and the single character Z is directly added to the order. The final output in this case is simply Z. These examples highlight how the solution handles special scenarios, ensuring correctness even at the boundaries of input constraints. Here, we are analyzing the time complexity of the solution by breaking it into three main steps. First, we create the graph and initialize the in-degree dictionary by iterating through all characters in all words. If the total number of characters across all words is C, this step takes C time. Next, we build the graph by comparing adjacent words to determine character relationships. In the worst case, each character in the shorter word is compared to the corresponding character in the longer word, and since the total number of characters is C, this step also takes C time. Finally, we perform a topological sort using Kahn's algorithm. Here, each character is processed exactly once, and for each character, its neighbors in the adjacency list are examined. Because the total number of edges in the graph is at most equal to C, this step also requires C time. When we sum these steps, the overall time complexity remains C. Now, let's summarize the time complexity. Adding the three steps together, the total time complexity of the solution is C. Next, we evaluate the space complexity, which depends on four factors. First, the graph is stored as a dictionary mapping each character to a set of its neighbors. In the worst case, the number of edges in the graph corresponds to the total number of characters, so the graph requires C space. Second, the in-degree dictionary stores an integer value for each unique character, and since there are at most C characters, this also requires C space. Third, we have the queue used in Kahn's algorithm for processing nodes with 0 in-degree. In the worst-case scenario, all characters could be in the queue simultaneously, so the space required is C. In addition to the graph, in-degree dictionary, and queue, we need to account for the order list, which stores the result of the topological sort. This list contains all unique characters, so it requires C space. When we combine all these factors, the overall space complexity is C. We can also evaluate the algorithm for different cases. In the best case, the input words are already sorted lexicographically according to the alien dictionary, so no edges need to be added. However, all characters are still processed, keeping the time complexity at C. In the average case, adjacent words are compared, and the graph is constructed as described, resulting in C time complexity. Finally, in the worst case, there are many dependencies between the characters, but the algorithm still processes each character and edge at most once, so the time complexity remains C. To further highlight the efficiency of this approach, let's compare it to a brute force method. A brute force approach would involve generating all possible orders of the characters and verifying which one satisfies the ordering constraints. This requires computing permutations of the characters, leading to a time complexity of O(C). In contrast, our current algorithm leverages topological sorting to achieve a far more efficient O(C) time complexity, which is a significant improvement for large inputs. Finally, we can mathematically justify the big O notation. Since every character and edge is processed at most once during both graph construction and topological sorting, and the total number of characters and edges is proportional to C, the overall time complexity is O(C). This linear scaling makes the algorithm highly efficient and optimal for this problem. When tackling the alien dictionary problem, there are several common mistakes to avoid. First, it's important to not assume that all characters in the input are connected. The input may not provide enough constraints to establish a complete order for all letters, especially if some letters only appear in isolated single-letter words. Second, be cautious during graph construction. The correct approach is to create edges only for the first differing character between two adjacent words, as this is what defines the order. Comparing all characters leads to invalid dependencies that could break the solution. Lastly, watch out for prefix relationships. If one word is a prefix of another, such as in the case of ABC and AB, the input is invalid since it's impossible to determine a valid ordering from such data. Recognizing and handling these scenarios correctly is key to solving the problem effectively. Another mistake to avoid is neglecting cycle detection in the graph. Cycles indicate that there are conflicting dependencies, which makes it impossible to determine a valid topological order. In such cases, your algorithm needs to correctly identify the cycle and return either an error or an empty result. Additionally, some solutions end up overcomplicating the implementation by relying on extra data structures or repeatedly sorting the graph. This increases the time complexity unnecessarily. Instead, a single topological sort using either BFS, such as Kahn's algorithm, or DFS is sufficient and efficient. Keeping the solution simple and focused on these algorithms ensures better performance and maintainability. These insights are especially valuable during interviews, where efficiency and clarity are crucial. To excel in solving this problem, pattern recognition is critical. This is fundamentally a graph problem that requires topological sorting, so identifying this early can save you time. Be prepared to clearly articulate how you construct the graph and traverse it. It's also important to consider edge cases, such as single-word dictionaries where no ordering constraints exist, words with the same prefix like ABC and ABD, and invalid inputs caused by prefix relationships. From a complexity perspective, constructing the graph takes O(C), where C is the total number of characters in the input. The topological sort itself runs in O(V plus E), where V is the number of unique characters, and E is the number of edges. Space complexity is also O(V plus E), to store the graph and track visited nodes. Understanding these complexities allows you to explain and justify your solution effectively. The alien dictionary problem shares similarities with several other graph-based problems, which can help you draw connections and improve your understanding. For example, LeetCode 207, course schedule, is a classic topological sorting problem where you determine if a valid course order exists. LeetCode 210, course schedule 2, builds on this by requiring the actual course order. Another related problem is LeetCode 329, longest increasing path in a matrix, which applies topological sorting in a grid-based graph instead of a word-based context. Lastly, LeetCode 444, sequence reconstruction, involves reconstructing a sequence using subsequences while adhering to graph and ordering constraints. Studying these related problems can deepen your grasp of topological sorting and help you recognize patterns across different scenarios. There are several approaches to solving topological sorting problems, each with its own advantages and drawbacks. A DFS-based topological sort involves performing a depth-first search on unvisited nodes, marking them as visited, and adding them to a result stack in the reverse order of their finishing time. This method is simpler to implement recursively but can run into stack overflow issues for very large graphs. On the other hand, a BFS-based approach, such as Kahn's algorithm, uses an in-degree counter to track nodes with no incoming edges and processes them iteratively. This method avoids recursion limits and is generally easier to debug, though maintaining the in-degree array adds slight complexity. Representing the graph as an adjacency matrix is another option, but it's not recommended due to its high space complexity of O(V squared) and inefficiency for sparse graphs. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make. Great job on completing this walkthrough. To summarize, we solved the alien dictionary problem by constructing a graph and using topological sorting to deduce the character order. Key takeaways include the importance of graphs in solving ordering constraints and the need to handle edge cases carefully. Thanks for watching, and don't forget to subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!